Grand existence, citizens of the universe. Welcome back to the reading of Einstein's Einstein, Philosopher Scientist's Autobiographical Notes. I will continue where I left off as soon as I get a confirmation that I'm recording live on the internet. Yes, I am. So give me actually one more second. Actually, I'll do it later. Alright, so picking up where I left off, I'm going to read the last two sentences and then go forward. So let me minimize myself here. That's not me. That's me. Alright, hopefully you can hear me alright. Put myself over here like last time. Got the German on the left, English on the right. And where did I leave off? Einstein said, if one puts up with the concepts of space, including geometry and time, without critical doubts, then there exists no reason to object to the idea of action at a distance, even though such a concept is unsuited to the ideas which one forms on the basis of the raw experience of life. However, there is another consideration which causes mechanics, taken as the basis of physics, to appear as primitive. Essentially, there exist two laws. One, the law of motion, and two, the expression for force or potential energy. The law of motion is precise, although empty, as long as the expression for the forces is not given. In postulating the latter, however, there exists great latitude for arbitrary, quote, choice, especially if one omits the demand, which is not very natural in any case, that the forces depend only on the coordinates and, for example, not on their differential quotients with respect to time. Within the framework of theory alone, it is entirely arbitrary that the forces of gravitation and electricity, which come from one point, are governed by the potential function of I over R. Additional remark. It has long been known that this function is the central symmetrical solution of the simplest rotation invariant differential equation, delta equals 0. Delta of something. I actually don't read Greek, I'm sorry, or Latin. Whatever that sign is right there, could be it's not a gamma, it's not a delta, it's not I don't know what it is. Maybe sigma? Delta of sigma equals 0. That's what I'm going to call it sigma, just in case he uses it again. It would therefore have been a suggestive idea to regard this as a sign that this function is to be regarded as determined by a law of space, a procedure which by the arbitrariness in the choice of the law of energy would have been removed. This is really the first insight which suggests a turning away from the theory of distant forces, a development which, prepared by Faraday, Maxwell, and Hertz, really begins only later on under the external pressure of experimental data. I'm not going to lie, some of that was confusing. I would also like to mention, as one internal asymmetry of this theory, that the inert mass occurring in the law of motion also appears in the expression for the gravitational force, but not in the expression for the other forces. Finally, I would like to point to the fact that the division of energy into two essentially different parts, kinetic and potential energy, must be felt as unnatural. H. Hertz felt this is so disturbing. In his very last work, he attempted to free mechanics from the concept of potential energy, i.e. the concept of force. Enough of this. Newton, forgive me. You found the only way which in your age was just about possible for a man of highest thought and creative power. The concepts which you created are even today still guiding our thinking in physics, although we now know that they will have to be replaced by others farther removed from the sphere of immediate experience if we aim at a profounder understanding of relationships. Is this supposed to be an obituary? The astonished reader will likely ask. I would like to reply essentially yes, for the essential in the being of a man of my type lies precisely in what he thinks and how he thinks, not in what he does or suffers. Consequently, the obituary can limit itself in the main to the communicating of thoughts which have played a considerable role in my endeavors. A theory is the more impressive the greater the simplicity of its premises is, the more different kinds of things it relates, and the more extended is its area of applicability. Therefore, the deep impression which classical thermodynamics made upon me. It is the only physical theory of universal content concerning which I am convinced that, within the framework of the applicability of its basic concepts, it will never be overthrown, for the special attention of those who are skeptics on principle. The most fascinating subject at the time that I was a student was Maxwell's theory. What made his theory appear revolutionary was the transition from forces at a distance to fields as fundamental variables. The incorporation of optics into the theory of electromagnetism, with its relation of the speed of light to the electric and magnetic absolute system of units, as well as the relation of the refraction coefficient to the dielectric constant, the qualitative relation between the reflection coefficient and the metallic conductivity of the body, it was like a revelation. Aside from the transition to field theory, i.e. the expression of the elementary laws through differential equations, Maxwell needed only one single hypothetical step: the introduction of the electrical displacement current in the vacuum and in the dielectra and its magnetic effect, an innovation which was almost prescribed by the formal properties of the differential equations. In this connection, I cannot suppress the remark that the pair Faraday-Maxwell has a most remarkable inner similarity with the pair Galileo-Newton, the former of each pair grasping the relations intuitively, and the second one formulating these relations exactly and applying them quantitatively. What rendered the insight into the essence of electromagnetic theory so much more difficult at that time was the following peculiar situation. Electric or magnetic field intensities and displacements were treated as equally elementary variables, empty space as a spatial instance of a dielectric body. Quote, well, not quote, italicized, matter appeared as the bearer of the field, not space. By this, it was implied that the carrier of the field could have velocity, and this was naturally to apply to the vacuum, or ether, also. Hertz's electrodynamics of moving bodies rests entirely upon this fundamental attitude. Oh, what happened? 2 seconds. You know I got camera problems. Where'd you go? I don't even know why I care about about my camera right now. There we go. At any rate, we got it. Alright, I digress. By this it was implied that the carrier of the field could have velocity, and this was naturally to apply to the vacuum or ether also. Hertz's electrodynamics of moving bodies rests entirely upon this fundamental attitude. It was the great merit of H.A. Lorentz that he brought about a change here in a convincing fashion. In principle, a field exists according to him only in empty space. Matter, considered as atoms, is the only seat of electric charges. Between the material particles there is empty space, the seat of the electromagnetic field, which is created by the position and velocity of the point charges which are located on the material particles. Dielectricity, conductivity, etc. are determined exclusively by the type of mechanical tie connecting the particles of which the bodies consist. The particle charges create the field, which on the other hand exerts forces upon the charges of the particles, thus determining the motion of the latter according to Newton's law of motion. If one compares this with Newton's system, the change consists in this: action at a distance is replaced by the field, which thus also describes the radiation. Gravitation is usually not taken into account because of its relative smallness. Its consideration, however, was always possible by means of the enrichment of the structure of the field, i.e., expansion of Maxwell's law of the field. The physicist of this present generation regards the point of view achieved by Lorentz as the only possible one. At that time, however, it was a surprising and audacious step, without which the later development would not have been possible. If one views this phase of the development of theory critically, one is struck by the dualism which lies in the fact that the material point in Newton's sense and the field as continuum are used as elementary concepts side by side. Kinetic energy and field energy appear as essentially different things. This appears all the more unsatisfactory inasmuch as, according to Maxwell's theory, the magnetic field of a moving electrical charge represents inertia. Why not then total inertia? Then only field energy would be left, and the particle would be merely an area of special density of field energy. In that case, one could hope to deduce the concept of the mass point together with the equations of the motion of the particles from the field equations. The disturbing dualism would have been removed. H.A. Lorentz knew this very well. However, Maxwell's equations did not permit the derivations of the equilibrium of the electricity which constitutes a particle. On the other hand, nonlinear field equations could possibly accomplish such a thing, but no method existed by which this kind of field equations could be discovered without deteriorating into adventurous arbitrariness. In any case, one could believe that it would be possible by and by to find a new and secure foundation for all physics upon the path which had been so successfully begun by Faraday and Maxwell, ... Accordingly, the revolution begun by the introduction of the field was by no means finished. Then it happened that, around the turn of the century, independently of what we have just been discussing, a second fundamental crisis set in, the seriousness of which was suddenly recognized due to Max Planck's investigations into heat radiation in 1900. The history of this event is all the more remarkable because, at least in its first phase, it was not in any way influenced by any unsurprising discoveries of an experimental nature. On thermodynamic grounds, Kirchhoff had concluded the energy density in the spectral composition of radiation in Hohlraum, surrounded by the impenetrable walls of the temperature T, would be independent of the nature of the walls. That is to say, the non-chromatic density of radiation, Q, is a rival function of the frequency V and of the absolute temperature T. Thus arose the interesting problem of determining this function Q parentheses V comma T end parentheses. What could theoretically be ascertained about this function? According to Maxwell's theory, the radiation, I think that is like a Q with the, not coordinates, but data points of V and T, otherwise frequency and temperature. Q is radiation, so radiation with this frequency and this temperature is what that means. What could theoretically be ascertained about this function? According to Maxwell's theory, the radiation had to exert a pressure on the walls determined by the total energy density. From this, Boltzmann concluded by means of pure thermodynamics that the entire energy density of the radiation is proportional to T to the fourth? Is that what that says? I think that's a 4. T to the fourth. That is the sum of Q, D, and V. In this way, he found the theoretical justification of a law which had previously been discovered empirically by Stefan, i.e., in this way he connected this empirical law with the basis of Maxwell's theory. Thereafter, by way of an ingenious thermodynamic consideration, which also made use of Maxwell's theory, Wien, I don't know, W-I-E-N, Wien, I don't know what his first name is, found that the universal function Q of the two variables V and T, so again, Wien found that the universal function of non-chromatic density of radiation of the two variables frequency and temperature would have to be of the form P is about equal to frequency to the third power multiplied by the sum of frequency over time. Frequency over temperature, I'm sorry, I'll say that again. P is about equal to V, the frequency to the third power, times the sum of frequency over temperature. Whereby, so F, sorry, I said, I'm fucking this up. P is about equal to V to the third multiplied by the function of V over T. So V, whereby the function of V over T is a universal function of one variable, frequency divided by temperature only. It was clear that the theoretical determination of this universal function was of fundamental importance. This was precisely the task which confronted Planck. Careful measurements had led to a very precise empirical determination of the function of F, of the function of the function. V over T is the function symbolized by the character F. Relying on, so if I say F, function F, that's what that means, V over T. Relying on these empirical measurements, he succeeded in the first place in finding a statement which measured which rendered the measurements very well. We've got a long equation here. P equals, I don't know, sigma times pi times h, which I forget. It's, god damn it. I know what h is. Times the frequency to the third over c to the third, it looks like. Multiplied by I don't even know. If you want to see the equation, look at the video. I'm not a goddamn physicist. I'm not a god-loving physicist. Alright. So, he rendered the measurements very well indeed, whereby h and k are two universal constants, the first of which led to quantum theory. Because of the denominator, this formula looks a bit queer. Was it possible to derive it theoretically? Planck actually did find a derivation, the imperfections of which remained at first hidden, which latter fact was most fortunate for the development of physics. If this formula was correct, it permitted, with the aid of Maxwell's theory, the calculation of the average energy E of a quasi-monochromatic oscillator within the field of radiation. And now you can see the formula for E here. E equals H times V over EXP. Man, I know what these mean. E is something and X is something, P is something, times HV divided by KT minus 1. Planck preferred to attempt calculating this latter magnitude theoretically. In this effort, thermodynamics, for the time being, proved no longer helpful, and neither did Maxwell's theory. The following circumstance was unusually encouraging in this formula. For high temperatures with a fixed V, it yielded the expression E equals K times T. This is the same expression as the kinetic theory of gases yields for the average energy of a mass point which is capable of oscillating elastically in one dimension. For in kinetic gas theory, one gets E equals R over N times T, whereby R means the constant of the equation of state of a gas and N the number of molecules per mole, from which constant one can compute the absolute size of the atom. Putting these two expressions equal to each other, one gets N equals R over K. The one constant of Planck's formula, consequently furnishes exactly the correct size of the atom. The numerical value agreed satisfactorily with the determinations of N by means of kinetic gas theory, even though these latter were not very accurate. This was a great success, with which Planck clearly recognized. But the matter has a serious drawback, which Planck fortunately overlooked at first. For the same considerations demand, in fact, that the relation E equals K times T would also have to be valid for low temperatures. In that case, however, it would be all over with Planck's formula and with the constant H. From the existing theory, therefore, the correct conclusion would have been the average kinetic energy of the oscillator is either given incorrectly by the theory of gases, which would imply a refutation of statistical mechanics, or else the average energy of the oscillator follows incorrectly from Maxwell's theory, which would imply a refutation of the latter. Under such circumstances, it is most probable that both theories are correct only at the limits, but are otherwise false. This is indeed the situation, as we shall see in what follows. If Planck had drawn this conclusion, he probably would not have made his great discovery, because the foundation would have been withdrawn from his deductive reasoning. Now back to Planck's reasoning. On the basis of the kinetic theory of gases, Boltzmann had discovered that, aside from a constant factor, entropy is equivalent to the logarithm of the probability of the state under consideration. Through this insight, he recognized the nature of courses of events which, in the sense of thermodynamics, are, quote, irreversible. Seen from the molecular mechanical point of view, however, all courses of events are reversible. If one calls a molecular, theoretically defined state a microscopically described one, or more briefly, microstate, and a state described in terms of thermodynamics a macrostate, then an immensely large number, say Z, of states belong to a macroscopic condition. Z then is a measure of the probability of a chosen macro state. This idea appears to be of outstanding importance also because of the fact that its usefulness is not limited to microscopic description on the basis of mechanics. Planck recognized this and applied the Boltzmann principle to a system which consists of very many resonators of the same frequency, V. Planck is a smart freaking dude to have realized all this stuff. The macroscopic situation is given through the total energy of the oscillation of all resonators, a micro condition through which determination of the instantaneous energy of each individual resonator. In order then to be able to express the number of the microstates belonging to the macrostate by means of a finite number, he, Planck, divided the total energy into a large but finite number of identical energy elements and asked, in how many ways can these energy elements be divided among the resonators? The logarithm of this number then furnishes the entropy and thus, via thermodynamics, the temperature of the system. Planck got his radiation formula if he chose his energy elements of the magnitude. The decisive element in doing this lies in the fact that the result depends on taking for E a definite finite value. This form of reasoning does not make obvious the fact that it contradicts the mechanical and electrodynamic basis upon which the derivation otherwise depends. Actually, however, the derivation presupposes implicitly that energy can be absorbed and emitted by the individual resonator only in quanta of magnitude h times v, i.e., that the energy of a mechanical structure capable of oscillations as well as the energy of radiation can be transferred only in such quanta, in contradiction to the laws of mechanics and electrodynamics. The contradiction with dynamics was here fundamental, whereas the contradiction with electrodynamics could be less fundamental. For the expression of the density of radiation energy, although it is compatible with Maxwell's equations, is not a necessary consequence of these equations. That this expression furnishes important average values is shown by the fact that the Stefan-Boltzmann law and Wien's law, or Wien's law, gonna be honest, it's spelled more like Wien, but I don't know, it's definitely German or something. It's shown by the fact that the Stefan-Boltzmann law and Wien's law, which are based on it, are in agreement with experience. All of this was quite clear to me shortly after the appearance of Planck's fundamental work, so that, without having a substitute for classical mechanics, I could nevertheless see what kind of consequences this law of temperature radiation leads for the photoelectric effect and for other related phenomena of the transformation of radiation energy, as well as for the specific heat of especially solid bodies. All my attempts, however, to adapt the theoretical foundation of physics to this, quote, new type of knowledge failed completely. It was as if the ground had been pulled out from under one. Einstein was theoretically rugged, with no firm foundation to be seen anywhere upon which one could have built. That this insecure and contradictory foundation was sufficient to enable a man of Bohr's unique instinct and tact to discover the major laws of the spectral lines and of the electron shells, shout out the electron shells, of the atoms together with their significance for chemistry appeared to me like a miracle, and appears to me as a miracle even today. That is the highest, this is the highest form of musicality in the sphere of thought. Damn. I'm going to read that last paragraph one more time and then we're taking a break. See you in part 3. All of this was quite clear to me shortly after the appearance of Planck's fundamental work, so that, without having a substitute for classical mechanics, I could nevertheless see what kind of consequences this law of temperature radiation leads for the photoelectric effect and for other related phenomena of the transformation of radiation energy, as well as for the specific heat of especially solid bodies. All my attempts, however, to adapt the theoretical foundation of physics to this new type of knowledge failed completely. It was as if the ground had been pulled out from under one, with no firm foundation to be seen anywhere upon which one could have built. That this insecure and contradictory foundation was sufficient to enable a man of Bohr's unique instinct and tact to discover the major laws of the spectral lines and of the electron shells of the atoms together with their significance for chemistry appeared to me like a miracle, and appears to me as a miracle even today. This is the highest form of musicality in the sphere of thought. That is page 47 of Einstein's Autobiographical Notes. The Philosopher Scientist, we're going to leave it there until next time. Grand existence, everybody.